afternoon. Warm welcome to another inaugural lecture from University of Moratuwa. So to start with that introduction to inaugural lecture from Professor P. Andreas, I kindly request Professor Chinta Jayasinghe to introduce today's speaker.
Thank you. Good afternoon, everybody. Deans of the faculties, distinguished guests, colleagues, ladies and gentlemen. It gives me a great pleasure to introduce Professor C.S. Lewangamage, a highly respected scholar and expert in his field. He graduated from the University of Moratuwa in 1998 with an honors degree in civil engineering with a first class. He obtained both his MH and PhD in structural engineering from the University of Tokyo, Japan. Professor Lewangamage is a distinguished academic who has devoted his career to the pursuit of knowledge and understanding in the area of structural engineering and has made significant contributions to his field through his research, teaching, and publications. With more than 18 years of experience in academia, Professor Lewangamage is highly regarded by his colleagues and students for his expertise and his dedication. After completion of his postgraduate studies, Professor Lewangamage joined as a bridge design engineer at GC Engineering, Houston, USA in 2004. After returning from USA, he joined the Department of Civil and Environmental Engineering, University of Ruhuna in 2005 as a senior lecturer. In 2007, he joined the Department of Civil Engineering, University of Moratuwa as a senior lecturer. Dr. C.S. Lewangamage became a professor in civil engineering, University of Moratuwa in 2021. He was a visiting academic of Department of Architecture and Civil Engineering, University of Bath, United Kingdom, and also a visiting academic researcher of Cyclone Testing Station, Townsville, Queensland, Australia. He also functioned as the competent authority at the Institute of Technology, University of Moratuwa in 2021. Currently, he is working as the project director for Science and Technology Human Resource Development Project under the Ministry of Education, funded by Asian Development Bank. He has conducted extensive research in the area of structural engineering with the special focus on wind and earthquake loading on structures, structural health monitoring, and structural retrofitting and strengthening. Development of large strain measurement system using image analysis, development of failure criterion for rubber and its seismic isolation bearings, development of wind loading map for Sri Lanka, development of low-cost online structural health monitoring system for civil infrastructures using wireless sensors, development of guidelines for design of engineered buildings for earthquake loading in the Sri Lankan context are some of his major findings as outcomes of his research. He is the pioneer in establishing a new research laboratory on structural dynamics and health monitoring at Department of Civil Engineering, University of Moratuwa. As a scholar, Professor Lewangamage has published more than 75 research papers in top-tier academic journals and conferences. He has also served as a reviewer for many leading international journals and has contributed to the development of new research methods and techniques. Professor Lewangamage won many awards of excellence in recognition of his outstanding research performance for several years from University of Moratuwa, Sri Lanka. In 2017, one of his papers on a statistical-based approach for demarcating a wind loading map for Sri Lanka won the gold medal for the best paper at annual sessions of Society of Structural Engineers Sri Lanka and secured the prestigious Mombasho Scholarship to pursue his doctoral studies at University of Tokyo, Japan, awarded by the Ministry of Science, Sports and Culture in Japan. He was the editor of the Modulus Journal of Society of Structural Engineers Sri Lanka in 2018 and has been an editorial board member of the Journal of SIDA from 2010 to date. He was a member of Executive Committee of the Society of Structural Engineers Sri Lanka in 2018. He is an international collaborator for the Tokyo Polytechnic University, Japan, and James Cook University, Australia, and the Sri Lankan representative for the International Working Group on Regional Harmonization of Wind Loading and Wind Environmental Specifications in Asia Pacific region. He has immensely contributed for the development of the Sri Lankan construction industry as an outstanding structural engineering professional. He has carried out more than 200 structural investigations and assessments that include the structural assessment on historical structures and monuments, and design reviews of high-rise buildings as well. So he also extended his services to the highway constructions in Sri Lanka in the areas of feasibility studies, structural design and reviews, non-destructive testing, damage assessments, and repair methodologies. He is a corporate member of Society of Structural Engineers Sri Lanka, corporate member and a chartered engineer of Institution of Engineers Sri Lanka, and one of the licensed structural engineers to certify medium-rise buildings. With all these achievements and positive contributions towards the continuous stability, growth, and excellence of university and the industry, Professor C.S. Lewangamage can be considered as a leading academic as well as a leading civil engineering professional in the country. It is my great pleasure to introduce Professor C.S. Lewangamage, a distinguished scholar, lecturer, and a leader in the field. I'm confident that his insights, wisdom, and expertise will be of great value to all of us, and I invite you to join me in welcoming him today to deliver his inaugural lecture as a professor on a timely topic, earthquakes, are we affected? Over to you.
Right, very good afternoon to you all. Thank you, Professor Mrs. Jayasinha, for very detailed introduction. And Vice Chancellor, Deputy Vice Chancellor, Dean of Faculty of Engineering, Dean, Faculty of Graduate Studies, Head Department of Civil Engineering, all other deans, heads, senior professors, the professors, my colleagues, students, all other academia, friends, and all others who are joining online. So I would like to welcome all of you for my inaugural lecture. Today I feel honored and privileged to address this gathering as part of this inaugural lecture series organized by the Faculty of Graduate Studies, University of Morocco. So I also thank Dean Faculty of Graduate Studies for inviting me for this lecture. So actually this lecture is dedicated to my family and all my teachers. Right, that the topic that I have selected today is hot topic. So these days. So I'm going to talk about earthquakes. That question is, are we affected? So my lecture will be a not highly technical one, but so anyone can understand. The content has several topics: the recent events, major earthquakes, what causes earthquake, earthquake hazards. So the problem that are we affected, how vulnerable our structures, the way forward. So national design guidelines and our research and our industry supports and collaborations. Yeah, I will start with this slide, the restless earth. So one of British geologists said that the history of any part of the earth is like the life of a soldier. Consists a long period of boredom and short period of fair. So any part of the world, so it can subject to natural events such as volcanic activities, earthquake, then earthquake-induced tsunamis, and cyclones, etc. So we are going to talk today the earthquake. So you see recent events and major earthquake. Just 1.5 months ago, that we had serious disaster because of Turkey Syria earthquake. So this earthquake killed over 50,000 people in both Turkey and Syria, and also damage or completely collapsed over 6,000 buildings. And so this earthquake occurred at one of the red boundary, and so there is very close to Turkey and Syria border that both countries got affected. So over 50,000 people died. So why? So this earthquake was particularly we call disaster due to unsafe buildings. So many of the buildings had collapsed due to soft story condition. What is soft story condition? So one level of a building that is significantly weaker in lateral rotation than stories above it, so we call soft story condition. So you can see that video that most of the buildings collapse in vertical direction. So that is basically the soft story conditions. The magnitude of earthquake was 7.8, and this happened in very early morning when people are sleeping. Then after a few hours, next day early morning, there is another aftershock, about 7.5 magnitude earthquake. Then over 10,000 aftershocks. All these event. So due to that, there are so many casualties. So this is when we are counting the if you see this the drone footages of this event, you can see the extension of damage. You can see it has happened in very populated areas, so that it was actually a natural disaster. So actually, when we are counting this death toll in the Turkey Syria earthquake, so Indian news agencies, so on 22nd of February, they gave a news. So they said that the major earthquake likely to hit in Himalaya, north part of India. So then parallelly, we had several events in Buttala, Vellava area that we had several tremors as reported. So due to this event, people slightly vigilant, and our media has given some priority for these news. With that developments, some of our scientists have given the controversial statement as well. So with this, we can see that several historical earthquakes that happened in the place that Indian scientists predict the recent earthquake, that is in Himalaya. So this is what happened in 2015 May in Nepal. So this is again the disaster for Nepal, and due to this earthquake, 2,500 people died. Lot of property damage, lot of building damage, and so this was a natural disaster for them. Then you see the history. You go to Taiwan, so this is developed country, and they have revised their design codes and continuously updating their design codes for earthquake loading, but still this event caused over 100 people dead. The reason is that collapse of few buildings. So actually, most of their buildings, so they have done strengthening, but this few building collapsed, and it became the disaster for them that during that event. So actually, what happened? So because of one of the building collapse, that 59 people died. So then, so after this event, actually, so that the structural they have arrested the structural engineer who have designed this the building. So actually, as engineers, or especially structural engineers, so we have huge responsibility to ensure the safety of the people. Again, if you go to Japan, so this is another event, and Japan, we know that, so Japan is located in one of the plate boundary, and but so they have, after 1995 Kobe earthquake, so they have revised their design codes and they are continuously updating. But still, you can see this earthquake happened in 2016, but still they got 30 plus dead and lot of property damage, especially that it was affected for their infrastructure system and landslide, the building damage, and so on. So now we can see that it doesn't matter where we are. So we have these events, and so we can have the disasters. Even we develop or underdevelop or developing. So doesn't matter that natural causes the events that we have to face. So actually, we can see that major earthquake always could be a disaster. So in our context, that an earthquake with magnitude over 6, we know that it releases large amount of energy and could be considered as a major earthquake. So now today, these days actually, this is very common, the term that earthquakes do not kill people, but buildings could do. So everywhere we can see this state. So what we are expecting, our buildings, our civil infrastructure to survive. So even after a major earthquake. So that means if you have earthquake more than 6 magnitude, that is still, we have to make sure that our infrastructure and buildings should be survived. So that is the collapse prevention of life safety condition. So we have to design our structure at least to make sure the collapse prevention, and then better if you can design at least for life safety condition. Then we can make sure that people will not kill. In addition to that, of course, we should have civil preparations when you have major earthquake. So we should have continuous monitoring and timely warning systems, education, strong disaster management system, and response teams be ready. Actually, to face this type of disaster event, so we need economic stability. So what will happen if you are not ready? The major earthquake could be a national disaster, and so we had this experience in 2004. So if you, with that background, if you discuss a little bit about earthquake, what causes earthquake? There are several causes. That tectonic plate and faults movement is a major cause of earthquake. So in addition to that volcanic activities, mine collapse, the underground explosions, reservoir-induced earthquakes, mainly that is due to the water pressure. So when we have a water pressure, that local faults can lubricate, that we can have earthquakes. Then nuclear testing. These are some of the causes of earthquake, but the major cause of earthquake are tectonic plate movements. You know that the earth crust, that is the outer layer of the planet, our planet, is made up of several pieces. So we call tectonic plates. So basically we have 21 tectonic plates. Out of that, so we have 7 major plates as indicated in this picture. So we know that these plates are constantly moving and interacting each other. Then, so we can have earthquake. So in this band where we are, so you can see that we are here and we are within the Australian plate, or we call Indo-Australian plate. But Indians, they used to call this as Indian plate. So we are here. So you can, this red line, you can see that these are plate boundaries. So when you talk about these plates and pole movements, we say that it can cause earthquake. So at plate boundaries, we can have different movements. So we can have the divergence, transformations, the convergence, and so with these movements, so it can have it can generate a lot of energy and with the earthquake. Then of course the plate boundaries also we can have the earthquake, but it can be in low magnitude. So we know that the boundaries between tectonic plates are made up of system of poles, and so but plate boundaries are always pole. We can define that way, but not all poles are plate boundaries. So this with these events, what will happen when you have earthquake at plate boundary? We can have energy propagation, so in form of seismic waves. Basically, so we have 3 types of seismic wave. The main one is primary waves, that is we call fastest seismic waves. That is first waves to arrive to the, so whatever the measuring station that we have established. Then the secondary waves, also we call shear waves, the slower than the P waves, and they arrive at the measuring station after the P waves. The problem is this shear wave, so the secondary waves are more destructive than P waves. The reason is they have high amplitude and frequency. So it can cause significant shaking as well, and then damage to the structure. The surface wave travels along the surface. These are slower seismic waves. So these waves can cause more damage because they travel close to the surface. So actually, for deep earthquakes, surface waves will be weaker because it's travel close to the surface. So mainly this secondary waves and surface waves can cause significant shaking and cause damage. So we know that we heard earthquake. When we heard about earthquake, so they tell us that the depth of the earthquake and basically epicenter distance. So in the plate boundary or pole boundary, when the earthquake happened, that location we call focus, then the vertical distance to the focus from the earth surface, that we call focal depth. So that is the depth of earthquake. Then the vertical projection to the earth surface from focus, that is we call epicenter. And so anywhere you are in the earth surface, that you can measure the epicentral distance. Then so we can measure the earthquakes. The basic idea of measuring earthquake is that simply you can set up a rotating drum on the ground, and if you can have mechanism to record the displacement of this drum is rotating with a known time, so that we can have displacement record. So this is the idea of the recording the earthquake, but now we have advanced instrument like seismograph, and so we can get the time histories of earthquake, the acceleration with time. So acceleration, the time history, so that is acceleration versus time of earthquake, we call time history. So actually what we need as structural engineers to design our structures is time history. With this time history, so we can develop our hazard maps. And same time, so we can develop so what is called response spectrum for a particular location, or particular the region, or for a country. So if you have these seismic hazard maps and response spectrum, then we can do our structural design for earthquake loads. The other things that the important thing that when you talk about earthquake, how you can describe the earthquake. So you can describe earthquake in two parameters. One is the magnitude, other one is intensity. The magnitude always says that amount of energy released to earth crust. The intensity indicates always how much downstream. So you see the magnitude, that is, so basically scale 1 to 10, the largest earthquake ever recorded, that is in between 9 and 10. And then, so basically this unit has the scale that always that energy released by earthquake about 30 times greater than the unit below. So that is the indication of the unit. So for example, if you take magnitude 6 earthquake, the releases 30 times as much as energy than magnitude 5 earthquake, actually. So that is, if you see magnitude 4 earthquake, so that is, if you compare 4 and 6, that is 900 times. Right? Usually we measure that magnitude in Richter scale. The intensity. So it is something that you feel, that is how much downside, and also that intensity will vary from place to place. So it is generally greatest near the epicenter, but gets smaller further away. Actually, no, the intensity is not measured in the instrument, but considering this effect on people and the structures, so we have a scale. So there are actually there are several scales, but the famous scale we call one is modified Mercalli intensity scale, and for Japanese they have what is called Shindo intensity scale. That is Mercalli scale that we have 12 points, but Shindo intensity scale we have 7 points. This is how you normally give the prediction of intensity. So if it is like contour map, each contour has almost same effects. But Japanese, they are predicting with numbers like this. So if you see the world largest earthquake, of course there are few. We have experienced this the fifth one, that is Sumatra earthquake, that is happened in Sunda Trench in 2004. That was fifth largest in history, according to the USGS. So if you see the earthquake numbers per year and energy release and the potential damage, so then if you see the magnitude versus potential damage, so you can see that recently we had tremors, so that indicate that it is in between magnitude 2 and 3 mostly. And actually this type of earthquake rarely felt by humans, and we are not expecting the damage. But in Syria earthquake, then now Indians they have predicted this earthquake will happen in the first 2 weeks of March, but still we are waiting. It didn't happen. And so this earthquake with magnitude 7 plus, so it can have damage, lot of chance of lot of economic impacts, loss of life, the damage for the buildings and so on. So there is the scale. But now we are talking about here in Sri Lanka that the earthquake with magnitude about 3 or maximum 4. So that is, you can see that how many earthquakes happen per a year like that. This about 100,000 per year. So that is that means we are not only the people that experience this type of earthquake. So the other people in the world also, they are experiencing this type of earthquake. Then if you see how much energy is released compared to this magnitude, you can see that if it's a big earthquake, that lot of energy release. So that's why it always become a disaster, right? Lot of energy and then lot of impact to the environment and the humans, right? Then if you just get the idea about intensity scale, that magnitude modified Merkel intensity scale, that if you have intensity scale 3 earthquake, you maybe you can recognize, but we don't expect damage. But you go for magnitude 10 earthquake, right? So we can have the damage. So mostly masonry structures, the foundations, right? That will be a disaster. So yes, will be a huge disaster. Is that if you have this magnitude intensity scale 10 earthquake. But still, if you compare further this magnitude, this is important because people to understand what we are experiencing in our country. That again, I'm repeating here that the magnitude scale 2.5 to 5 earthquake so often felt and only cause minor damage. That is important. Again, according to this source, that estimated number by year is 500,000. Right? It's a big number. Right? So what we felt here in Sri Lanka, that is what felt in other part of the world as well. Now, if you go to our plate now, we are in Indo-Australian tectonic plate. Now you can see that earthquake around us. So this map indicates earthquake magnitude more than 4. So you can see very clearly plate boundary. In this plate boundary, we have a lot of earthquake, right? Lot of earthquake, but within the plate also we have earthquake. But if you see the magnitude earthquake magnitude more than 7, you can see that the few numbers, not many, right? We can see this around here, Sunda Trench, that there are some earthquake, and also it is not you can see here, but in the northern part of the India, we can have this type of earthquake. So that means that mostly what we have is the earthquake magnitude more than in between 4 and 7. So now people also talk about this earthquake predictions. That is also important topic, and that when you predict earthquake, so we can have long-term predictions and short-term predictions, right? When you talk about long-term prediction, of course, we can have a chance to tell that recurrence interval of earthquake. Then we can have hazard maps, so as long-term predictions. But this type of thing we can use for structural designs. But most importantly, what we know is short-term predictions, like especially like earthquake, right? The short-term predictions we can have post-earthquake warning or precautions. But these short-term precautions, I don't think we can measure here in Sri Lanka. But if you are living near to the plate boundaries, then we can have this type of short-term precautions, like seismic, the POSOCs, and then different strain effect like deformations, or table changes, gas emissions, this type of effects. Then also that we believe that the before earthquake, that there is a change in the animal behavior and also types. And with this data, actually, if you are living near the plate boundaries, where we got a lot of earthquake, that we can have some idea. But since we are living middle of the plate boundary, that we are not expecting that direct impact on the interplate earthquake, that I don't think we can the predict the earthquake. So actually, this is very important that I would say it is not currently possible to predict exactly when and where an earthquake will occur and how large it will be. That is not possible. But some scientists or seismologists can estimate where earthquake may likely to occur based on these measurements. But we have to be careful when we have predicting earthquake as well, right? So there's be some socio-economic impacts, right? But it is not valid for us, but mainly but for other part of the world where we got a lot of earthquake that will valid the changes of property values, the business activities, that evacuations, right? People might feel evacuate and people might panic, feel that panic, and of course we have to be careful that will destroy the scientist livelihood as well. So if you only make the earthquake, right? So now, so this is about earthquakes, right? I think you hopefully you got idea about what is earthquake and what is the impact on the earthquake. Then if you go to the earthquake hazards, so we can have two types of hazards: the primary hazards and the secondary hazards. Actually, we are not worried about primary hazards. It can give all displacement, down shaking. Actually, we are not much worried about down shaking, but we are much worried about the secondary hazards, like tsunamis, the landslide, liquefactions, the structural failures, fire-induced damage, and so on, right? So these are directly impact to the environment and to the humans. So we are really worried about these secondary hazards. So the one of secondary effect is tsunami. We had this experience in 2004 after the earthquake at Sumatra and at Sunda Trench, that we had this tsunami. The over 30,000 people died in Sri Lanka. Then these are some of the pictures, right? So after tsunami in Sri Lanka, so you can see clearly this gold bus stand and this parallel train incident, and so on, that we got a lot of damage. Then most importantly, now we have recent experience in this Turkish Syria earthquake that building kill people, right? So how building vibrate and kill people during earthquake, right? When you have major earthquake, of course, we have ground shaking, and then this is ground shaking means always the energy. That because of that, you got energy input to the structures, and the structures going to vibrate, and of course, there's potential damage or collapse. Actually, the severity of shaking and resulting damage to any structure or building, and depending on various factors. So that is the strength of earthquake, the location, and also duration of earthquake. Actually, if you have long duration earthquake, of course, you have more damage because it generates more energy. Not only that, the structure type. So if you have your structure is regular or irregular, right? So damage will be different. Of course, regular structures, right? So we expect, if you are properly designed, we expect no damage. But if your structure is irregular, that so it is suspicious for more damage because of mainly closure. Of course, we have to have your structures. You have to construct with quality material, and so you have to use the quality construction. And also the how you it depends on how your structures has been designed. Then you see this common mode of building failures during earthquake. The one of major failure that we seen in even the Turkish Syria earthquake, this soft story collapse, right? So this ground level, at the low level of those that doesn't have enough lateral load testing capacity to take the loads, especially wedge shear. Due to that, so you can have this type of failures. We call this soft story condition. The other failure mode is liquefaction. What is liquefaction? When you have earthquake like the more than magnitude 6, that it releases a lot of energy, and then we have the lot of ground shaking. With that one, especially this poisonous soil, like sandy soil, right? The flow like liquid, right? If your structure have shallow foundation, that you are put that foundation on sandy soil, right? Then foundation will affect due to the bigger. Then of course we can see this type of instability of building and then you can water. Right. The other one is use of unnecessary masses. Right. If you use big masses in the structures, of course it absorbs big force. Because you know that because of acceleration of the structures, you got inertia. You got inertia forces. The inertia means mass into acceleration. That is a basic equation. Mass into acceleration, that you got big force. When you have big mass, of course, there's chance of damage. Then the torsion. So this is the some of effect of torsion, especially when you are think of irregular structures, right? Our architects sometimes think about outsets. They like it, but as structural engineers, we don't like that, right? We don't like it, right? Especially if you are designing a building in earthquake regions, seriously you have to think about it, right? We like to have regular building, right? Continuous mass distribution, continuous distance distribution throughout the structure. So if you have irregular building, so you can have torsion, right? Even the advanced softwares cannot predict sometimes torsions, so that we are expecting damage. Then the effect of vertical discontinuity, right? When you are designing building, you are planning building, right? So you like to have the car parks at the lower floor levels, then at the top you like to have apartments. So in that case, of course, you have to change the structural grid through a transit plate. So in that case, you have to be really careful that because you are changing your structural grid. So in that case, if you don't design your structure, especially lower floors, that we can have this type of damage, right? Then short column effect. So it's a common damage again. The short column always has high stiffness than other columns, that it can absorb the big force, so that we can have this type of damage. Then the progressive collapse. So that is again common type of the failure that, so the floors can one collapse onto another, so that we can have overloading, and then we can have this type of progressive collapse, right? We have seen some progressive collapse in this Turkish area. Then stone beam weak columns. Actually, this is not our designs for earthquake. We don't design our structures with stone beam weak column, right? The other way. But if it is designed is this way, that of course building will collapse because it can form plastic hinges in the column. The formation of plastic hinges can cause failures. So that is true, but as structural engineers, we allow plastic hinges to form in the structures, but we have to make sure that we have to create a right place, so that so we can dissipate energy, right? We introduce ductility to the structure, that so allowing formation of plastic hinges, but we have to make sure that we have to do it in the correct place. Right. With that, the information that really that we want to know, that are we affected, right? So if you see historical seismic activities in Sri Lanka, that so I have just here listing the selected activities, not all. One event in the earthquake that occurred close to Colombo, the 14th April 1615, had about 2,000 casualties, than 200 houses suffered damage. Actually, this is published in Lisbon in 1660. Right? So this, I think, the largest event that ever recorded in Sri Lanka, according to this. But there's another event, the 1938, says that failed storm in Western Province and Central Highlands. And then this event in 1993, one person died and mine property damage. Then when you see that historically there are many tremors in and around the country, and these tremors mainly felt in southeast, southern and central highlands of the country. Of course, we had experienced tsunami in 2004 due to major earthquake in Sunda Trench, and that is not direct earthquake but secondary effect due to earthquake. But history says that minor earthquakes are possible, but moderate earthquakes with magnitude 5 to 6 would be rare events. That is what history says to us. So, if you think about interplate seismic activity around Sri Lanka, right? We now, as you saw this image earlier, that we can see very clearly this the plate boundary or plate boundary, right? So, actually, Sri Lanka is located in the northwestern region of this Indo-Australian plate. Actually, this to talk about this interplate seismic activity around this plate, that is, we have to think about two places. One is the Himalayas to the north. Actually, this Indo-Australian plate meeting Eurasian plate, which is part, and then says that pushes against each other, so that we can have earthquake, right? You can see that lot of earthquake there. And same time that Sunda Trench to the east, so around here you can have a lot of earthquake. So that is, we call that the plate deformation, there is subduction. Because of this movement, so we can have both earthquakes and tsunamis, right? So actually we are worried about, if you talk about interplate earthquake, these two locations, right? Himalayas and the Sunda Trench. Same time, this some seismologists discuss possibility of formation of new plate bound to the south of Sri Lanka, right? But it can happen in geological time scale, not in years. So that actually we are not too much worried about that. Even we can see some, the earthquakes around that region, but still I think we don't have to worry about that. The problem is what will happen if major earthquake hit at plate boundary close to Sri Lanka, that is in either in Sunda Trench or in Himalayas. So actually what we are expecting, the significant damage within the radius of 200 to 300 kilometers from the location that earthquake can hit, right? Actually, we are very far away from those locations, right? So that means, so we are always expecting the most destruction to the building within that radius. So we are safe. Then of course, due to this type of major earthquake in this region, of course, vibration effect would be felt because of that seismic waves can travel from there to right Sri Lanka, so that we can have vibration impacts. So actually, if we have various weak soil conditions, of course, we can have some amplification, right? Higher degree of vibration in our structures. So actually, if that is the case, that we are expecting very low energy input to the foundation of our buildings, right? Then if you have this type of low energy input, of course, it is hard to induce the inertia in the waste structures. So that we are not expecting any structural damage due to earthquake in plate boundaries, right? That means that recent statement on the earthquake 8 Richter scale Himalaya could damage building in Colombo is not true, right? So we are not expecting that, right? Then of course there's a good chance of we can pick that the the vibrations using sensitive seismographic instrument. That can happen. That actually, if earthquake happened in this Sundat range, of course, we can have tsunami. Right? There's chance of having tsunamis. Right? It happened in 2004. Actually, what we have said that, but what we expect, there's a remote chance of some building of Sri Lanka to amplify due to this induced vibration. Sometimes people might feel like earthquake. Right? That is the two things can happen. Of course, we can have big tsunami, and right, people might feel some vibration, that is maximum in our building, and people might feel earthquake. That is a maximum thing that can happen if we have earthquake in plate boundary. Then, so the another type of earthquake we call intraplate earthquake. That earthquake happened within the plate boundary, right? Then, of course, it can happen due to local faults, and it can happen any place without fault, right? It is difficult to predict time, location, and magnitude, and generally it is rare event, right? These are two good examples that the 5.9 magnitude earthquake hit in Newcastle in Australia in 1989, and also this Maharashtra earthquake in India 1993. This Newcastle was considered as no risk area before this earthquake actually, and there's a lot of property damage after this, but I think there's no serious casualties there, unfortunately. Then actually this Maharashtra earthquake also, that place is far away from the Himalaya, and that it report that 10,000 people, right? So what we are expecting, that interplate earthquake impact to the Sri Lanka. But if you see interplate seismic activity in Sri Lanka, right? If you take Sri Lankan map, that this indicate actually you can see this red one, with the magnitude 2 scale earthquake that we call actually not earthquake, tremors. Low magnitude earthquake we call tremors. So we have tremors, right? That is not happened just month ago, just 2 days ago. It happened all the time, right? We have seen this, right, about this map, right? This is scale tremors, especially this central highlands, this southeastern part and southern part of the country. We have these tremors, right? But if you see this map around Sri Lanka, you can see that there is high intensity earthquake zone. Concentrate this northeast part of the India and also southwest part, right? That is we call normally Indian fault zone, right? Actually, if interplate earthquake happen in this region, this Indian fault zone, but still we are far away from that zone, and but we are not expecting significant impact to there may be some impact to the northern region of Sri Lanka. But other important thing, that the Sri Lanka was in this Gondwana land in 200 million years ago. That old Sri Lanka, India, this Africa, the Antarctica and the Australia all together, right? So then during that time, so there is a fault that actually run from Trincomalee to the Sangoda. So that is in Hambantota, and but thing is that we consider this fault is dead now, right? Inactive, right? But historically, of course, there are many tremors in and around this the fault. But still, sometimes what we have experienced in Sri Lanka, we have seen that it is around this fault boundary, that running from Trincomalee to Sangoda. So in that case, even it is dead, but we call it is dead, but still we can have chance of having the minor tremors around it, right? That might be a reason. Then, of course, there are always reservoir-induced tremors around this central highland of the country. That is main reason is, I think, the pressure, water pressure that can lubricate the local fault so that can create tremors, right? Then this is sometimes this controversial statement that minor tremors could reduce risk of major earthquake. But here I am talking about outside the plate boundary, right? Because this energy, when you release the energy, we can reduce the risk. But if you go to the plate boundary, this might not true that we can take this as a sometime as a that is a warning for the major earthquake, right? This we can tell in other way as well, right? So then what we are expecting tremors, minor tremors in Sri Lanka means that I feel that they reduce the risk, right? It is better to have minor tremors. Then effect of interplate earthquake in Sri Lankan context, right? But we are expecting only interplate earthquake impact to the country, and of course, it is very natural for it to be felt by people, right? Of course, some minor damage can expected for non-engineered structures, right? Engineered structures that we build without any technical inputs, right? Then even we have this Indian fault zone, but still it is difficult to identify that it is active enough to cause major earthquakes, right? And but even historically, Sri Lanka has not recorded any significant event, right? So in that context, that earthquake with magnitude 4 to 6 Richter scale will be rare event for us, right? Still, if it happened, that epicenters could be far away from Sri Lanka, right? So in that case, that maybe that can expected due to this fault around this Manarik zone and Comorodian Ridge and other Indian fault zones, right? Still, epicenters what we are expecting far away from Sri Lanka, right? Of course, sometimes tremors with this magnitude 2.4 can be expected in eastern, southern, and central highlands of Sri Lanka due to local geological behaviors and also the existing reservoirs and the central highlands specific, right? That is what we have experienced in recent past. So, what we have to say that chances of any significant damage to the engineered structures under interplate earthquake would be minimal. Again, that our buildings still are safe. We expected some damage to the non-engineered structures, so unreinforced masonry structures. Actually, it has been observed even during this reported tremors, and we have seen some masonry wall cracking and some foundation damage that is in minor nature or single-story houses. In summary, the possible earthquake impact to Sri Lanka. So we have to say that there is no evidence that Sri Lanka would be hit by major, right? So I am putting major earthquake for our context magnitude 6, but in other places they are putting in the 7. But our context we can say that if you have 6 more than 6, it will be major for us, right? Then there is always risk of tsunamis due to major earthquake, especially as from the trench, and so that risk is there always. So the interplate earthquake that could occur at Indian Ocean and South Indian Port, that we can have interplate earthquake due to seismic activities outside the country. Then what we expect tremors in between 2.5 to 4 due to local geological behaviors that we are expecting in southern part, south, east and central highland. So that also due to we can expect these major seismic activities at outside Sri Lanka as well. Even sometimes we can have we can report this as this much of scale even due to interplate earthquake, right? So that means that there is a remote chance of occurrence of moderate earthquake in between magnitude 4 and 6, but we have to ready for that, right? We are ready for this, right? So there is always remote chance of some building in Sri Lanka to amplify earthquake into such places so that people might feel evacuated. Of course, we are expecting this, right? Actually, we are not expecting significant structural damage to our engineered structures, even under interplate earthquake happened in the pit. We don't expect because our structures we are designed based on the the codes actually we practice normally Redis code. I think if you practice our code with our codes, our structural design, I don't think we can have structural damage. Then, of course, we expect some the damage for the non-linear structures, 400 post-masonry structures, right? Then, if you go to the other important topic, that's seismic monitoring, then hazard assessment procedure. So actually, this is a very important thing that you think about earthquake design, and we are ready for earthquake, that we need seismic monitoring, right? So basically, we have 4 seismic monitoring stations located in Sri Lanka, then Mahakandra, then Pallekele, Hapmon, and Buddanga, right? So these seismometers actually they are connected with the global network as well. That is operated by GSMB. And so, but the problem is whether we have adequate numbers for seismic monitoring, right? That is the question. Then, of course, as engineers, if you want to design our structures, so we need hazard assessment for our country. Actually, there are 2 studies, recent studies in 2019 and 2020, and so they have produced kind of a hazard maps or hazard parameters for Sri Lanka. So actually, one of the important parameters that we have to determine to think about structural design is a peak down estimation. That is for a particular return period. Normally, we use this the bottom line is 475 years return period. Or when you talk about this peak down estimation. So actually, this 2020 study, but done by Peradeniya group of researchers. So they found that our PGA values for especially for Colombo area is 0.1 G. That is actually big value, and that prediction I must say that is somewhat conservative because we are working with limited data. Then also they propose response spectrum. That is also that the data that we need to do dynamic analysis. If we want to analyze our structures more accurately, that we need response spectrum, right? Response spectrum can be you can propose for a location, for a region, or for a country. So that is what we have seen. This is actually almost equal to the Indian response spectrum, right? That's what they have proposed. And the thing is that this even 2019 study also they have similar value, 0.11 G PGA value for Colombo, right? But some studies even before that they are predicting some low values PGA for Colombo, but you can see that is contradictory. And anyway, so what I feel that is the conservative values, and to design so this much of course for PGA, of course our structure will be super safe for earthquake loading, but still, so what we are recommending for this Colombo, if you use this PGA value as 0.06 to 0.08, that is for important structures, that will be adequate. And for outside region, that Colombo, that maybe you can think about not unpopulated areas like isolated structures, we can think about 0.05 G PGA for design. Then with anyway, we have kind of a seismic hazard assessment for Sri Lanka. Then of course we can work with this. The problem is how vulnerable our structures. For that basically buildings, and then we have bridges. So the mostly that we are concerned, right? So of course, if you think about buildings, right? Based on our previous discussion, so we can see that what we are expecting, the earthquake, it will felt by people in the building. But in that case, people might feel discomfort, right? May post that feel like evacuation, right? Then, if you have earthquake in between, like magnitude 3, 4 earthquake, we are expected some minor damage for non-indigenous structures or basically domestic houses, right? So again, we consider this as buildings, right? Then, so we are expecting some significant damage for non-engineered building due to moderate earthquake, right? That is the worst that we are expecting. That is earthquake in between M4 M6. Then we are expecting no structural damage to the engineered building, even without considered any earthquake loading during design due to moderate earthquake. Still, we can tell that even our engineered building, I don't think that we will get the structural damage if you design according to the British codes or Euro codes, right? Even with this earthquake in between magnitude 4.6. But that is, we talk about structural damage, not non-structural damage. Talk about structural damage. Then we are not expecting no notable damage for engineered building. At least you could consider that earthquake detailing when you are doing designs, right? Of course, we are not expecting any damage for the building if you are designing our buildings according to the recognized code, right? So that is the building. If you go to the bridges in Sri Lanka, especially our expressway, the elevated expressways and flyovers, right? Of course, they are on stone foundation, mainly on piles, right? That the many foundation would be on rough, so hard soil in our highways, and only few will be on sandy soil or soft soil, right? So what we are expecting or less earthquake magnitude less than 6, in that case we are not expecting liquefaction effect in Sri Lanka, right? In addition to that, of course, our bridges have wider piers and abutments, so that we are expecting minor damage or no damage during the earthquake that we are expecting in Sri Lanka. Actual recent highways could have considered earthquake like Port Texas Highway and Canal Bridge. So that's already considered, right? So that means our bridges, flyovers, elevated expressway generally will be safe for earthquake magnitude less than 6. That's what we are expecting in Sri Lanka. But in case, since we are expecting the moderate earthquake in Sri Lankan context, so we have to build our houses, bridges by adopting earthquake resistant features, so that the losses in extreme re-event still would be minimal, right? So that if you can spend the 10% of structural cost or 5% of overall cost, right, we can do better, and then we can have earthquake resistant structures in our country. The way forward, what we have to do? Actually, we should have seismic hazard mitigation mechanism for Sri Lanka. This is what I am recommending. We need few more seismograph stations to be located. At least we need one in Colombo and one in Japan, right? Then, of course, the government organizations such as GSMB, NBRO, Disaster Management Center, SLSI, universities need to work together to develop comprehensive policies on earthquake risk mitigation and implementation at ground level. It is important that we have to implement the whatever the policies at ground level. So otherwise, of course, there are some guidelines developed by DMC and even NBRO, but that is not went up to the ground level. So DMC Sri Lanka need networking with regional disaster risk prediction and mitigation centers. That is important. And the professional organization like ISL, Society of Structural Engineers Sri Lanka, universities need more proactive to provide necessary knowledge and training for the engineers and technical personnel related to earthquake in this country. So all engineering faculties in the country need to be strengthened with research facilities and personnels. We know that, so even we don't have much facilities related to the earthquake. Then of course we need national guidelines on earthquake design and the construction standard. Especially I'm recommending that even UD guidelines can be revised to incorporate in some earthquake design features, and so that has to be done. Then now we need strong civil preparation system, right? And it can consist of education, disaster response system, evacuation plan at high risk areas, and then fire hazards due to earthquake, and communication protocols, very important, that people are telling different things, different people, and legislation. Even give the media statement, so different people are telling different things. So especially the related to earthquake that people may panic. That we have seen even the tremors that type of situation. People were vigilant and the media also that gave priority for these events, tremors. And of course, we did timely warning, but not for earthquake. I think for tsunamis, right? Of course, we have to study the possible impact due to secondary effect, tsunamis, flooding, and landslide. And of course, our important structure need to be checked for probable moderate earthquakes. That is major dams, reservoirs, right? Even this overhead tanks, and we have big reservoirs and belongs to the Sri Lanka Water Board, and the important building and major breaches, right? We have to take adequate remedial action, and if it is required. Then, of course, we need earthquake safety assessment system of building in high-risk areas, the especially populated areas. We have seen that don't put it after this Syria earthquake that there are lot of damage in populated areas because of that. So many people died. Then, of course, we have to do this risk assessment exercise for these high-risk areas, and we have to take adequate remedials if necessary. So at least now, so after these tremors, people call and ask from us, so at least what to do, right? Even I think at least this simple type of thing that should go to the ground level, right? What we have to do before, during, after, right? We don't have this type of complicated things, but still we have to develop this type of thing for our Sri Lankan countries, right? Then the design guidelines. Right, earthquake design guideline. Actually, we have worked on this, and so when you think about designs for earthquake loading, so people always we talk about the performance-based designs, right? So some buildings we can design for operational level even after major earthquake, or we talk about moderate earthquake in Sri Lankan context, but some clients can say that I forget my building if major earthquake hit, right? So in between we can do the designs, right? So for example, the hospitals in Sri Lanka should be operational even after the major event, should function. But some building private structures, but we have to make sure that people will not die, but it will not collapse, and we can have casualties, but we have to make sure minimum safety. But after that, we can forget the building, right? So in between, we can do the design. So that is we call performance-based design, right? So actually, the reason the code of practices actually try to incorporate this performance-based into the design standards. So when you think about specific design building in Sri Lanka, actually we can think about that consequences of failures, right? Under three categories. So significant effect to the safety of environment, right? So under that category, we can have schools, large building, dams, and so on, right? Then damage to the critical national infrastructures, right? The emergency services, health, energy, public services, and so on. Then, of course, economic consequences, right? So actually, we have to protect large economic centers, right? Harbors, airports, right? Highways, and so on, right? So if you think about the consequences of failure for this under these three categories, so we can formulate our design. Of course, there are different code of practices we use for specific designs of building. Then these are the famous around us, that FEMA, so that is US standards, and then Eurocode, and Indian standard, and Australian standard. Actually, Eurocode and Australian standard, so we teach in the universities, and our students, they know how to use that. Then actually, that's why I told that we teach these two codes in universities, Eurocode and this Australian code, right? So that there's the screening process of building to be designed for earthquake loads, right? So in that case, I'm not going to go for detail, but if you think about building in very low seismicity area, that we don't have to think about design for earthquakes. But if you are in high seismicity areas, of course, we have to do the design. But same approach we can see in both codes, but they are using different parameters sometimes. This is soil and the seismic hazard levels, right? Both codes have the same concepts. But we like to use Eurocode 8, but we are recommending to develop national guideline based on the Eurocode 8. So why Eurocode? We have to, we are recommending Eurocode. One thing is for consistency purpose. All other standard, design standards in Sri Lanka, now we are developing according to the Eurocodes. We are formulating our Sri Lankan national annexes, that we cannot have different code for earthquake code, but better have, right, the Eurocode for that. Then, of course, restriction and cost-effective solution can be made using Eurocode, because this is the Eurocodes are mostly based on fundamentals and then fundamental research, and so we can have better solutions than other codes. Then, of course, we can have our own code with Eurocode 8. We can have our national annex. Then we can have national design guideline for the earthquake loading for Sri Lankan context with inclusion of our local characteristic, right? So that's why we are recommending the Eurocode 8. So actually, then we can have screening process, the low seismicity that we can define this value. At actually should be can have good discussion with our scientists, and then we can formulate whether we need specific design within this the bottom line. It will be 0.04 G or not, maybe 0.05 G. So we define. So we don't need the specific design. Then if it is in between 0.04, 0.08 PGA, then we do only static check and do seismic detailing. Of course, if you need the important building, that we can go for if your PGA value is more than 0.08 G, right? So you can do the design according to the codes. Then, of course, we can have according to the consequences of failures of our structures, then we can have different classes of structures, right? Then based on the performance levels of the structures as well. Then this different important classes, we can design the earthquake for different return period. So this 475 may be the bottom line, but the different important classes we can have different return period, right? Then so when you think about this, since now we are saying that 475 years return period PG value for Colombo is 0.1 G, then we have to think about what is the PGA value for when we have 1,500 years return period and also 2,500 years return period, right? Then so this is what we have basically proposed for informed level of the building in Sri Lanka context. So actually there are 4 classes, and so basically if you in import class level 1 building, that we don't have to go for the earthquake design, but these are basically agricultural building, isolated structures, and maybe some domestic structures. But if you go to the import class 4 buildings, right? So it includes the import buildings and especially the medical facilities and hospitals, some the even police stations, like that. Also that even dams we can include in under this category, but that is not building, but right, we can include on this category. So this is the in between. Of course, we can have our structures to be considered for the design. Then when you calculate in this different PGA values for different return period, we can use this equation. I'm not going to explain this. It's too much technical. And but finally, with that equations, we can have the proposed value depending on the return period. For different return period, we can propose the PGA values. If it is 475 years, we say that 0.08 G for 1500 years return period, we can have 0.12, and 2500 years return period, we can have 0.14 G. Right? We use this import factor for import depending on the import level of building 1.5 and 1.8, right, to increase the PGA value. Then, of course, with this different classes, when you have different PGA value, we can have our elastic response spectrum, right, for Sri Lanka, and then depending on the right how you design your structures, how you introduce ductility to your structure, that we can create what is called design response spectrum. Then we can use that for the design using Eurocode 8. So either you can use the static method or dynamic methods. Especially that regular structure, generally you can go for static method, but irregular structures, of course, we have to do the dynamic method of analysis, right? Either time history analysis or response spectrum analysis. So that is so much technical, but I am not going to discuss that. So this is summary that relate to the national guidelines. So Sri Lankan national annex to the Eurocode 8, so need to be developed. I think the SLSI has to get the leadership on this, and with the other professional and government organization, and need to work together. Of course, we have published some guideline in this publication, and also that we can initially we can use this seismic hazard map proposed in this research study. Right? Actually, with more data, of course, our seismic hazard map need to be updated, because we have seen that the predicted values, PGA values, is conservative, highly conservative, and also we have to look at the practical scenarios that should be suitable for our country. When you are proposing, when you use for applications, that we have to seriously think about practical scenarios, especially the cost of structures. Then, of course, Eurocode 8 can be used with earthquake detail manual published by Society of Structural Engineers Sri Lanka, and also that even Eurocode 8 itself has the detailing guidelines. Of course, that is about earthquakes, and I think I have answered that the question that whether we have affected. And so, if you go to our research, we are working on the research on this area. We do interest support and collaborations. So we have this laboratory as our head has indicated, the structural dynamic and head monitoring laboratory in the Department of Civil Engineering. So we want to develop the internal facility attached to this laboratory as well. But unfortunately, we had this economic downturn of the country that we couldn't succeed with this proposal. But in future, we are planning to have internal facility for University of Moratuwa. Then, of course, these are the research that we are doing in this laboratory that relate to the earthquake. Then, of course, we do research related to the structural strengthening and the renovations. Then, of course, this is something related to the work that I have done in Japan, and so we work for this development of this material for seismic isolation, especially for the bridges. Then these are the modeling and full-scale testing. Then, of course, we are not only working with the earthquake, but we are working with the wind, with collaborative studies, with, for example, cyclone testing station, James Cook University of Australia, and we have done some testing there. And then, of course, we propose wind map for Sri Lanka that currently this map is being used by our engineers. And also we are working with the structural health monitoring in our laboratory that we have developed a low-cost structural health monitoring system for our structures, right? So now we have tested this, the development, developed sensors, and now they are actually these are low-cost ones, and then actually we can use this for the measurements, the field measurements. And also we have a small staking table that we have simulation staking table in our laboratory, and we are doing research based on that. actually related to the structural damage estimation and the health monitoring. Of course, we do a lot of industry supports, and we provide technical expertise to the industry, and we do design reviews, and also a lot of non-destructive testing that damage assessment and strengthening and so on. And of course, we do industry collaboration. That is recent past that we propose. We have proposed this modular bridge and retain wall system with ICC that we can complete this bridge within 3 days. So unfortunately, that we couldn't implement this application because of the country situation. And then of course we are doing collaborations with different research groups around the world, and we are strengthening research capacity of University of Malta. With that, so I have acknowledgement, of course, this journey that I have to acknowledge my late parents and my family, my brother and 2 sisters, my wife, Deepika, 2 daughters, Upuri and Uttali, all my teachers. Actually, I have to mention my A-level mathematics teacher, late Mr. Sompala, all my lecturers, especially I have to mention that my undergraduate supervisor, my great teacher and mentor, Professor Sanjay Singh, and my construction guru. So actually, I call guru that engineer U.S. Karunaratne. My postgraduate supervisors, Professor Masato Abe and Professor Yosu Fujino, and all my students and friends. Right. So then, thank you very much. I finally thank so those who attend for this lecture, and also thanks for Professor Ajit Alvis for organizing this event and inviting me for this lecture. Okay, thank you very much.
Thank you, Professor Lewangamage, for that insightful and comprehensive speech about earthquakes and how an earthquake is formed and how the damage is done, and also specifically about how Sri Lanka is affected and what Sri Lanka needs to do in order to prevent potential damages in the future as well. Now, I would like to invite Dean, Faculty of Engineering, Professor Udayanga Hemapala, to give a memento to mark this glorious occasion to Professor Lewangamage. With that, the 14th inaugural lecture has come to an end, and we wish to thank our sponsors who made this event a possibility. We have Cargill's as our event sponsor, and Daily FT as our print media sponsor, and the Sri Lankan Scientist as our social media sponsor. And finally, we would like to thank all the participants for participating in this lecture. And signing off, I'm Udesh Dangala. Good evening and goodbye.